Can you hear me? Great. Welcome to the last session of the day. This session is on action recognition, and we have 5 papers. The first paper is on real-time temporal action localization and untrimmed video by sub-action discovery. And unfortunately, Rui, who's the first author, couldn't make it, so I'm going to present in his place and ask myself a question at the end of the session. No one else does. So I think everyone here is familiar with action recognition in video, but for most people, when they think about action recognition, what do they really mean? They mean, given some pre-segmented clip, I want to classify it as, skydiving versus biking versus salsa, things like that. And that's kind of an artificial task, because it's very rare in real-world applications someone's going to give you that kind of a task. Now, that task can be useful for a variety of other things, but really the more practical task, at least in my opinion, is something like this, where you're given a YouTube video and someone tells you, can you find me all the instances of high jumping or tennis swings within there? So the idea is that the video may contain multiple instances, and your goal is to temporally localize them, if not spatially temporally. So in this talk, we're going to focus on how do you do temporal localization in video in a computationally efficient manner, so that you can do that at real-time speeds. So the motivation is that for actions like sports actions like long jump and so on, they actually consist of what we call sub-actions. So sub-action might be that there's a long jump that consists of someone running and then jumping. And what's interesting is that within a class, the different sub-actions actually exhibit a fair degree of variation. So ideally, you could imagine one could exploit this fact. And then, of course, not all the segments that exist among these are equally distributed. So if you take something like long jump versus high jump versus javelin throw, that initial approach looks very, very similar. So the initial sub-action for the class is similar, but then the final action might be very distinctive. So if your goal is to take video and kind of chop it up into small equal segments of video, you can't simply ignore this fact. And the question is, in this work, what we look at is, can you actually discover these sub-actions in a fully automated way and exploit these sub-action models to do better localization, but do it all in a very computationally efficient manner? So the stuff that I'm going to talk about today doesn't actually involve deep learning, but it's complementary to it. Might be the last non-deep learning stuff out of it. So the overview of the pipeline is that the training phase, we're going to do this weekly supervised discovery of sub-actions, which involves grouping them from these action parts. And there's an iterative procedure for updating these sub-actions based on the data. And then in the testing phase, we need to apply these sub-action models to identify candidate regions where there may be multiple of them, and then try to assemble them together to create these actions in an efficient manner, which we solve using a network flow idea. So let's actually look at it in terms of pictures. So what you have is you want to chop your training videos into equal length segments initially. So that's because a frame by itself is too small, but you get maybe 0.3 seconds or something. So that's a little bit of time to give you these equal length segments. And then since in the training data you have the actions that were localized, you can ignore the ones in the background, leaving you the ones left over. These are the kind of segments that correspond to the action of interest. Now, note that there may be multiple instances of them, and of course there may be the different sub-actions are all kind of grouped together. So the question is, how can you then take these equal length segments and assemble them into action parts? So this kind of grouping procedure is a little bit like clustering, and that's why this formulations are similar, but it has the constraint, obviously, that you want it to ensure the sequential ordering. So in other words, you want to say, given the equal length segments, which ones can you assemble together to create these parts from which you could assemble the sub-actions? And this is some kind of segmentation in time that gives you the ingredients that you need to create the sub-action models. And so the sub-action models themselves can then be leveraged to create individual models for the sub-actions, but because it's weakly supervised, you don't have to grab the label saying, this is the approach part of the long jump versus the final part, you need to do some tricks. And in this formulation, it's a little iterative procedure that trains little, in this case, SVM models for pairs of adjacent subactions, and then using these learned SVMs, you can adjust the boundaries. It'll be easier to see this in pictures, but this is the overview of the algorithm. All right, so let's look at what these subaction things are doing. So given a video like this, you first gone and chopped it up into the equal length segments. So these segments are each small enough that, in general, they don't contain multiple subactions, is the idea. So they're on the order of a fraction of a second. And there are enough of them that you can then assemble them together to get these parts. So in this case, we've shown you what would happen with this grouping procedure, the blue, green, and red are potential parts. Now, the parts themselves may not each correspond to subaction. It could just be, this is what the grouping gave you. So in many ways, the hope is that the parts have done a good job kind of separating the subactions. And you can refine that in the next page anyway, to take advantage of any errors. So if you do that, and you do that for all the videos for a given action in your training set, you will end up seeing something like this, where now the initial part of each of the different actions, each of the instances actions, is hopefully regrouped and so on. And that lets you build, these things are called parts. And now we can try to assemble these parts to create subaction models. So what you do, you look at adjacent pairs of these parts, and similarly on the other side. And then from that, what you can do is you can cluster together the parts that look similar across the various actions. Across the various instances of that action. In other words, that helps you understand that for an action like long jump, all the approaches look somewhat similar, whereas the jumping part looks similar across the instances. And once that's done, you can start training the initial models for that subaction itself, given this, treating this as kind of pseudo-label training data. And once that's done, you can then iteratively refine it to do things like here. You can notice that that by adjusting the boundary here, you can actually improve what's going on. So in other words, just because the submodels initially were trained to these parts doesn't prevent you from then refining that and actually adjusting the boundaries, and thus getting a better subaction model in the next iteration. So once that's done, that lets you create subaction detections in a fairly straightforward manner. In other words, there's a kind of a clearance term that says how well does this subaction match in terms of these features, and in this case we're using IDTF features. And then does it match the length of what I expect the subaction to take? And then, of course, you can then, your goal is to then take a combination of detected subactions to say, is there support for the action as a whole? In other words, does the subaction, do they occur in the right sequence, do they occur in the right spacing, and so on. Again, easier seen through pictures. So, given a test video like this, in this case it's a high jump video, you can run all your subaction classifiers in parallel. And so here we're going to show you the ones that are relevant to this action. So you can see that the subaction power ones are looking at high jumps, long jumps, and I think some golf swings and spikes. And you can see that the subaction ones, the little peaks that you can see, for instances with subaction classifiers, have determined that there's a high likelihood of that happening, and the ones which are low, like golf, never really activate. All right, so let's zoom in on a region there, corresponding to the ones relevant to high jump, and see what's going on. So now in this one, you can see that there are multiple different detections for each subaction. And that's because you could adjust that subaction duration and position and get different scores. So the question is there support for the high jump action? And if so, what are the subaction detections that you should combine to get that detection? And so here's where the network flow comes in, and you try in a dynamic programming way to identify the best set of subaction detections, and then that gives you a final score, not only for the subactions, but also for the action itself. And so then that's basically the algorithm. So we use IPA features, we optimize them for speed, and similarly the Fisher vector computation was optimized. And then in the lengths of the segments, they're kind of fractions of a second that we apply. So the results on the on TUMOS data set are quite promising, and you can see with the latest studies, you can see the impact of what happens if you don't use the parts, which is singleton one, and then if you don't optimize, as I showed the little, if you don't iteratively optimize, you can see also the degradation that we get. So in other words, the little components help, and it's an efficient system, and we see promising results also on mixed action. So here are some examples. You can see the temporal localization is showing up as just labels there. This particular method doesn't do spatial localization. And then in terms of running time, it can process videos at about 40 frames per second using this approach. And if you're curious about the running time, clustering the segments and updating sub-actions, you can see the time, and the total time for training is actually also really, really small. So that, from that perspective, it may be an attractive method for people to use even as a baseline for action localization. So, in conclusion, we've proposed a novel algorithm to take the action detection problem and break it down into this sub-action with these sub-action models, and we exploit the temporal structure of these sub-actions to both in terms of appearance and the duration in order to build these action localizers. And it's very computationally efficient, enables real-time action localization, so I encourage people to give it a try. Thank you very much. Questions? Yeah, go ahead.
So you don't have to ask yourself?
Yeah, thank you.
I was wondering, actually, because you're saying it's semantically meaningful, but when you have very extreme viewpoint changes, is it detecting the same sub-action semantically, or is it really going with just a segmentation, in temporal segmentation, and you have significant bits?
Yeah, that's a good question. I know that the speaker is active. Hearing? Yeah. Right, so the question is to what extent is semantically meaningful? And that really comes down to the features. And things like IDT features have only a limited degree of invariance to viewpoint changes. And so because that's what's being used in grouping and clustering, it's going to be dependent strongly on that. Now, in the case of the videos that you typically see on YouTube, like the sport type videos, they do have canonical things like long jump. People typically film it from the side rather than head on. But I think that's a fair question. Nothing within our algorithm makes it more robust than viewpoint changes, for instance. What we are somewhat robust is the duration, for example. If different people run for different lengths of time, that can be captured because of the way in which the action is assembled. It's not just average food over that entire segment. So temporal variability is accounted for, but not can the next speaker please come up and set up in case someone else has another question? I'm happy to answer as well. Yeah, there's a question back there.
On the previous slide, you mentioned it's real time, but it's something like thousands of seconds, or is it milliseconds?
No, the timing that was shown in that previous slide is the training time. And so that's actually showing that even in terms of training, even though we iteratively train these little SCM models, they're very, very fast. In terms of execution and inference time, it's 40 frames per second, and so that's not an issue. And that includes the feature computation as well. Great. Next speaker, please.
All right, let's take this one again.